Hey guys, it's JM. My friends over at Solidigm have sent me some P44 Pros to test out. And I convinced them, I said, well, that would be stupid to test one drive because there's all kinds of reviews on the internet that test a single drive. So I said, you guys should send me four drives. And so I'm going to do four drives in a RAID 0, and this is a perfect opportunity to test out some of the RAID functionality on the Threadripper Pro that AMD sent me. I've been wanting to test out actually some of the AMD NVMe RAID. I obviously am mostly a Linux user, and I've all the RAID functionality and software RAID works very well. So I wanted to see if this hardware RAID actually worked out. I learned a lot of things and remembered a lot of things about Windows RAID. Haven't used RAID in Windows in ages, so there's some bad news and some good news. Finally got some stuff working after a few back and forth. So we'll go through some of that, and we will look at some of the performance of a 4-drive RAID 0 in Windows as well as Linux, and of course Plotty performance. We're going to do a quick summary of the testing for the folks that don't want to watch the whole video. I tested the Solidigm P44 Pro on the AMD Threadripper 5000 and in 4 drives in a RAID 0. And so Windows RAID sucks. I started at Windows. I was hoping to try to do this whole thing in Windows to test the AMD RAID, and I was going to test Windows RAID versus AMD RAID and all this stuff. And Windows RAID obviously sucks. There's no trim in RAID 0, so performance is going to start out really nice and then just get abysmally bad very fast. Storage space is made for redundancy. It's not really set up for performance. And then I actually spent a lot of time trying to get this RAID Expert 2 to work, the AMD integrated RAID for NVMe. The installation process is a little tricky. You have to basically, for every single NVMe device, like replace the driver from the Microsoft Inbox NVMe driver with this AMD RAID driver. Performance was not great. I had it performing good once, and then I couldn't reproduce it. The random write performance was always really bad. Random read performance was like limited to a couple 100,000 IOPS. It was really, really bad. There's no smarter admin pass-throughs. So you can't do any low-level stuff to the drives, which you really need for benchmarking. You really need to be able to reset the drives to the factory default, fresh out of box state with an NVMe format, especially when you're doing benchmarking. The dashboard, the GUI would be nice to have some SSD stuff in there, like health monitoring, endurance, and temperature. And then, the secure erase from the tool actually does a full overwrite, which is not what you want for an SSD. Now I moved the setup to Linux after doing a day or two of testing with Windows and giving up, and the Linux performance actually performed very well. The 4-drive RAID 0 Linux performed and scaled extremely well, especially on sequentials. So the P44 Pro, the sequential read and write performance are very good. The SLC cache performance is extremely good, 7 gigabytes a second read, 6.5 gigabytes a second sequential write. And the post cache speed, after it's exhausted a couple hundred gigabytes of cache that you can get out of the writing performance in SLC mode, are actually still very good. You get 1.5 gigabytes a second, so that's extremely positive. The 4-drive RAID 0 put up amazing numbers. It worked really well in this little adapter card I had, and then the mixed workload and random write performance. I did my enterprise kind of script where it filled up the drive sequentially and then ran these random tests, and it didn't perform great in these mixed workloads or random write workloads, but it's a consumer drive. It's not meant for those. The performance in Linux was actually extremely good. The 4X P44 Pros in RAID 0 with a queue depth of 32 is able to get like 1.4 million IOPS, so about almost 6 gigabytes a second of 4K random read. This is very, very good. Random read 4K is actually scale with queue depth. The more queues, the more commands in the queue, the more random, the more parallelism on the drives. Again, a random read is picking a random LBA on the span of all the 4 drives. And so that was extremely positive and expected performance. The sequential reads were actually very strong, right? We get to almost 25 gigabytes a second in a queue depth of 4, which is like a very real workload kind of thing. Like a couple file transfers, a couple things in parallel, easily get to this 24, 25 gigabytes a second sequential read. The sequential write, again, the pre-cache, the SLC caching is 6.5 gigabytes a second per drive. You're not really going to hit that if you're doing sustained sequential workloads. So I'm doing this test that's a lot of sequential writing. It's just an FIO test. And so this was able to get to about 5 gigabytes a second. So that's again about 1.5 gigabytes a second per drive. And this is pretty strong performance out of a consumer drive. So overall, I'm pretty pleased with the performance in Linux RAID. So summary, I ran Bladebit disk on this platform, and this is again my Threadripper Pro. I actually really like this Lenovo ThinkStation P620. It's pretty small, it's quiet for what it has. I had some PCIe issues, but I was able to get around some of them by using different adapters and setting some stuff manually in the BIOS. The bifurcation on this PCIe Gen 4x16 card down to 4x4s was very easy. Just do it in the BIOS. This is running 8 channels of DDR4 3200 megatransfer per second, 64 gigabyte DIMMs, and so if I do a RAM plot on this system, I get 4.6 minutes or 280 seconds. If I did the 4X P44 Pros in RAID 0 and just did 100 gigs of cache, I got a 9.4 minute plot. And then again, this is simulating if you didn't have 512 gigabytes of RAM, if you had 8 DIMMs that were 16 gigabytes, then you could have this kind of config where you'd be able to run 64 threads. And this was the configuration I gave for Bladebit disk. Now the P44 Pros, 1 terabyte with no cache. I got some variance on the runs, but actually still performed pretty well, which means the bandwidth was keeping up with 64 cores on this Threadripper Pro. Now I ran one drive with cache and no cache, and obviously with no cache, it was 19.8 minutes. So obviously 64 cores is way too much for one terabyte consumer NVMe drive. With 100 gigs of cache, I was able to get it down to 12 minutes. This is pretty reasonable. I did add a P5510 just for comparison, comparing an enterprise drive versus this 4-drive RAID 0 on the consumer side. So with no cache, one P5510 does a 12.4 minute plot with Bladebit disk, and then with 100 gig cache, it goes down to about 10. So overall, the performance of Bladebit disk in this 4-drive RAID 0 was actually pretty great. It's a very good fit for Bladebit disk because it's sequential read and writes, and unfortunately, I did see some variation run to run, and just because of the SLC cache, you're going to see that on a consumer drive, where you're not going to see a lot of that on an enterprise drive. But overall, I think this is a pretty interesting config. Again, because you can get these 1 terabyte drives for $100, and so putting 2 of these in a RAID 0 on a platform is going to be pretty nice for a lot of people that do some plotting on. The P44 Pro is the newest high-performance NVMe drive from Solidigm. This is the first Solidigm drive that is using the SK NAND components. There's a lot of really interesting things about this drive for Chia specifically that we'll dive into. But the first off, it looks like an excellent drive just all around, just for consumer workloads. You're right, the 1 terabyte drive with SLC cache can do 7 gigabytes a second read, 6.5 gigabytes a second sequential write. Now, the interesting thing we'll look at is the post-cache write speed actually looks like it's very good on this drive, which will mean it'll hold up pretty well in Chia plotting performance, especially with something like Bladebit disk that's writing sequential. And the TBW, pretty standard for a consumer NVMe drive. This looks like a 3,000 cycle PE drive. But as we saw with most of these 1 terabyte drives that are 3,000 cycles, we actually saw a bunch of Samsung drives get up to like 5 or 6 petabytes written before they even started to slow down a little bit. And so the 750 TBW is the JEDEC rated workload for the WAF and the TBW. Often, what does that mean? Well, that just means it's kind of the worst case. Often you'll see 2 to 5x that in a regular workload if your write amp is low and you have trim enabled. And that's just the rated TBW. After you get to the rated TBW, oftentimes, as I mentioned, we saw NAND basically go 2x or even higher than that. So I would not be surprised if we saw 4 or 5 petabytes at least out of this thing. Well, actually, I'm going to do some endurance testing, so maybe we'll make it that far in the testing where we can actually beat up a drive pretty good and see how it holds up. But besides that, pretty standard. Also, low power modes for a laptop, which is good, but you don't need any of those if you're using these on a desktop. The interesting things we're going to look at, and I'm just taking a look at this Tech Power Up site that did one of the deeper reviews, is they do use this new SK Hynix Gen 4 controller for the consumer side. It looks like it's really high performance. It's an in-house controller. They do use DRAM on this. It looks like a couple gigs of DRAM up on the 2 terabyte drive, which is pretty standard for a high performance drive using onboard DRAM. And they are using the SK Hynix 176 layer 3D NAND, which is super fast. The other really interesting thing about this drive I mentioned is this post-cache write speed. So everybody knows consumer drives are very fast if you're doing like a short bursty workload because they're designed for mostly idle time. But the majority of consumer workloads like gaming, like office, like content creation you're just moving one big file and then the drive sits there mostly idle for the most of the time. So these SLC caches are very good for moving stuff into the drive fast, and then when the drive has idle time, it moves it to TLC or other media, in the background. So you can see they've done this test where they're just writing to the drive and find out how much you can write before the SLC cache gets exhausted, and it looks like a very large amount, almost 300 gigabytes. Totally gigabytes written before it starts to drop off, which is amazing on this 2 terabyte drive. But even on the 1 terabyte drive, it got to 200 gigabytes, which is, so if you think about our performance in a 4 drive RAID 0, we have 4 drives. If 4 of them have a cache of 200 gigs, we could potentially write 800 gigabytes before we start seeing some slowdowns. And we will go see if we really make it that far. But even the post cache write speed is very, very good. So this drive on paper, again, the things you care about for chia plotting performance are sustained sequential write speed and read speed, because in Bladebit disk, it's switching back and forth between sequential read and write really fast. You're reading a bunch of data off the drive, getting it into memory, sorting it, doing these matching and all the compression and stuff like that you have to do in the plotting, and then you're moving it back to the disk in these buckets. And so the drive has to do these bursty sequential reads and writes, but lots and lots of writes, so it just looks like continuous writing. And so this drive does appear that it should be pretty good at that workload. So with that, I'm going to go into some of the AMD stuff, because we spent a lot of time. I spent a lot of time getting this set up for the last couple of days, and I'll go through that. So now, we have these drives over here, and now if we wanted to do a Windows software RAID, we could go to new striped volume, go to next, and then we could add our little 1 terabyte drives in there, and even format it, form a quick format. P44 is what we have. Yay, convert them to dynamic disks and blah blah blah. Now this, as you'll see, is actually not a very good way to do Windows RAID. So the drive comes up and it's nice and happy here, and you can see here it comes up in PC as 3.72 terabytes. We have the RAID of 4 drives, but unfortunately, if you go to properties, and it's a little hard to see here, but if you go to tools, optimize, it says P44 optimization not available. So Windows RAID does not support trim in RAID 0, which basically kills the performance of the drive. As you saw with, even if you have a little bit of data on the drive needs trim to basically know from the host which LBAs, which blocks are not being used anymore, so that it can free them up and do garbage collection. If you don't have that, then the drive just always thinks that the data coming from the host is good data, that it's storing user data. So that's bad. So this, if we ran a benchmark against this this array, it would actually look very good, but the performance would fall off almost instantaneously after you fill up that first 3.72 terabytes. So we're not going to do that. We're going to delete this volume and make it go away. And in the meantime, we are going to go to the Windows Store and try to see if we can find this AMD RAID expert thing. Let's see, AMD RAID. Let's see if it pops up here. AMD RAID expert. Okay, so because we have the driver, it theoretically should work here. So I enabled it in the BIOS and then created an array, but it didn't show up in the operating system. And then you load the driver from Lenovo or AMD. I'm using a Lenovo P620. You load the AMD NVMe RAID driver and it doesn't work. And I kind of figured out finally that you have to not load it on just 1 or 2 NVMe controllers, but you have to load it on every single NVMe controller for it to work. And so it's a little clunky. You actually had to go in here to Device Manager and right-click on the normal the normal Windows NVMe driver devices. These are the NVMe controllers, and you'd have to go into here and go to Update Driver, and then search for the driver in the AMD folder, and then it'll like find this AMD RAID bottom device. It's not very intuitive. And then so after you do that on every single drive and then restart, then it finally shows up and lets you run this RAID expert. And again, this is a little clunky. It does, you can see all the drives. You can see my 4 1 terabyte drives here. Solidigm here, P44. So what you can do is, again, I guess it wasn't that hard to create the volume. You just go in here in array, create, click on the 4 drives, read and write cache is fine. Zero create. I'm worried what they actually do when you do zeroed out, but I'll show you what's going to happen here. If we go P44 and create, then you'll see we've created this volume here, RAID volume of the 1 terabyte NVMe drives, and it's showing up as 4.1 logical. That's good. So now the device shows up here in disk management. We can initialize it and format it, and that's fine, whatever. We'll call it P44. And quick format in Windows is good. Remember, this trims the entire LBA span when you do a quick format. That's good. And it's kind of hard to tell if it actually works there. And so what you can do is click on the P44 and hit Properties, and go into let's see, Tools, Optimize, and you can see it here. P44 needs optimization. This will trim all the LBAs and make sure everything's in a nice, good, healthy state. When you are testing a new device, this is a good thing to do. Now, I found out when I was doing this that the old Windows software RAID still does not support trim. I think the storage spaces does, but the performance is a lot different. Storage spaces isn't really for performance; it's really for redundancy and backup. So that's good. At least that they got trim and RAID 0 working. Is a good start. That's trim is the most important thing for SSDs to keep the drives performing well and the endurance good. All right, so now you can see here we have our RAID 3 P44. It's got 4 drives, and now it's showing up now as disk 2 in our in Windows. So we can initialize it if we want, create a partition. But let's run that same FIO test now to disk 2, which I think we always make sure if you're running something to a physical drive. Actually, hopefully it doesn't let you do this to your boot drive, but physical drive 2, physical drive 2. We're not using a file system yet. We will, of course, when we need to start plotting, but we will just run this here. So one thread with queue depth of 256. And disk 2 is writing at 6.7 gigabytes per second. So one of the theories here is maybe we're not giving it enough juice, right? Maybe we're not giving it enough workers or threads here. So we could actually come in here and give it some a number of jobs here. We can juice that up to 8 now that we have, well, I guess we'll just say 4, because we had 4 drives. This was doing pretty good before with 4, so we'll save 4 jobs. And so now let's run the same thing with 4 threads. So 4 threads are independently doing queue depth of 256 sequential write, and you can see here we're getting not very good write speed. All right, I caved and installed Ubuntu on here, and I'm much happier now. We're installed Ubuntu 22.10, which is using the 5.19 kernel, and this is still the P620 with the Threadripper Pro in there. What I'm doing is just running Bladebit disk right now. You can see here I'm running this run 2 right now is kind of in the middle of running. But you can see here in phase 1 now with no, I'm not using any cache. We're easily hitting, 9 gigabytes a second write throughput, 7 gigabytes a second read throughput. We can check here on a node exporter that's we're probably seeing the same kind of disk bandwidth. If we go to here and storage disk last 30 minutes, we can just go to like last 15. You can see MD0 is hitting 4 gigabytes a second disk bandwidth. Now what's tricky on here, you can see the confusing part is you'd say, okay, this is weird. Node exporters only reporting that I'm using about 4 gigabytes a second write and 2 gigabytes a second read bandwidth. It's like 6 gigabytes a second total bandwidth at this peak for Bladebit disk, and you can see these numbers are much higher. So what happens is actually Bladebit disk will read a bucket into memory. So if you have 64 buckets, you can just take the table size, which is like 13 gigabytes divided by buckets, and you have your bucket size. And then you read that bucket into memory, you do all this stuff to it, you do sorting, distribution, matching, and then you pop that bucket back. Now, you can see it's doing that really fast. It's bursty. So you send the bucket over the PCIe bus, in this case over 4 drives because we're in RAID 0 over storage to the CPU. The CPU does all the stuff and then has to write the bucket back. So all that reading and writing, Bladebit disk does it sequentially, but it does it really fast. And there is time in between there, and these are called context switches. And so you can see here to get about 4 gigabytes a second average write bandwidth over here, then you actually do need a little bit more bursty bandwidth. So you can kind of think about, a good rule of thumb is a total plot writes 1.4 terabytes of host writes, just about. And so if you take that and divide it by the amount of time that you want to target for your plot, you're going to have at least 2x that amount of bandwidth to actually hit that plot target. So if you can see here, we're getting close to finishing. This first one, I did have one finish with Bladebit disk in about 8.5 minutes. And so actually the run one, I didn't actually record that one, but then the next run, it was 10 minutes. So I guess I'll see what happens with this third run. You can see here, it's just running full blast here. But yeah, this is much better, with, I'll do some FIO testing after this, but it does look like with FIO, we're hitting, the rated read and write speeds of a single drive it's scaling pretty well to RAID 0, which is good. It's what we want for plotting. Okay, so we're going to do a sequential write test with FIO now that we've done a little bit of plotting, and I'm seeing some weird stuff as far as variation in the plotting times run to run on disk plot. So we'll see if that's related to the disk or something. But yeah, I suppose it's not CPU temperatures because I've done a ridiculous amount of Bladebit in memory plotting on this system and I've never seen any variation whatsoever. I mean, even with every different version of Ubuntu, it's like 280 seconds for a plot. That's like period. So we'll go to a screen called FIO, and we're going to run if we cat sequential.fio, you'll see super basic script. It's just going to run a 128K queue depth 256 and 2 threads sequential write for 120 seconds, and it's going to write it to this log. And it's going to run it to MD0, which is a RAID array of the 4 P44 Pros. And so we'll just do sudo fio sequential.fio. And so we'll see here, it starts at, so 24 GIB is, if we go back to, this is GIB as well. So dstat's showing 24 GIB. So 25 should be actually pretty close to our theoretical limit, right? So each one of these drives pre-cached with 6.5 gigabytes a second, SLC times 4, so 26. So actually we're hitting exactly the limit. And I suspect, if you remember, a single drive was 1.5 after post-cache. It should go down to about 6 gigabytes per second here in a little bit. And we can check, Grafana takes a minute to update, but dstat and the FIO will certainly update in real time. So we'll go back to our FIO, and as we can see here, it's dropped exactly to the post-cache TLC limit. So it's exhausted the SLC cache, now writing to TLC, and cool. So this is, at least good news, is that we are getting performance that we can explain and understand pretty well. Sometimes it's hard in RAID arrays to get the right queue depth and the right number of threads to kind of max out the drives, because each RAID array, depending on the different workload, you might want a different stripe size depending on if you're doing randoms or sequentials, if you're doing small block or large block. So when people ask me what's the right RAID stripe size, well, for SSDs, usually it's kind of small because normally TLC SSDs use a 4K indirection unit, which is the logical to physical mapping between host LBAs to physical place on the NAND. So if we look at a sequential read with 2 threads and queued up 256, you can see we're actually getting our full 28 gigabytes a second out of this array. So that's good news. Yay, 27 GIB. So yeah, looks like Linux MD RAID scales extremely well for sequential performance, which is kind of what we care about for Bladebit disk right now. we'll do some more random testing and other fun benchmarks here later, but this was just a good start to get us to understand. And if I've learned anything over this last week, it's really been how frustrating RAID in Windows is, and just how bad the disk management is. You can't do anything low level to the disks. You need to be able to format the NVMe drives. You need to be able to send trims to the commands. You need to be able to do all that stuff. Like, you can't have an NVMe RAID stack that doesn't support that stuff, or else you're just gonna be dead in the water when you hit some of these weird corner cases. It's already weird enough to try to benchmark drives. So with that, yeah, it's been fun testing these for a few days. I've learned a lot about why I remembered that I hate Windows RAID so much, but this has been a lot of fun testing these drives, and so thanks Solidigm for letting me test these out, and looking forward to doing some more testing. Bye-bye. I ran a script last night on a 4-drive RAID 0 using MD80M. This FIO script just runs through different queue depths, different workloads, random read, random write, 70-30, which is like 70% read, 30% write, and then it trims it and then does a sequential prep and then sequential read and write. Now, when you look at this data, this compared to like a typical enterprise drive, I'll show you kind of what's standing out as weird here. So random read scaling with queue depth, that's totally normal. As you can see, as we go from queue depth 1 to 2 to 4, 8, the performance of the random read goes up. That's totally expected. As you have 4 drives and you're picking a random LBA anywhere in the span of those 4 drives, the more commands you issue, more threads, more queue depth, the higher the performance is going to be. It's just the way it is. When you're doing a queue depth 1 of random read, the performance is always going to be slow, because it's just whatever the latency of the drive whatever the latency of that drive is to get you that 4K request. And so you can see here, as we scale up the random read IOPS, go from 59,000 at QDEP1, to looks like 1.4 million at QDEP32. So that's good. This is QDEP32, 1.4 million is very good. If we ran this test with QDEP 64 and 128, I expect we probably see some more scaling there. Now, this does not shine. Obviously, it's not an enterprise drive. The drive was filled with sequential data first, then doing random writes on top of that, and the write amp goes very high. You can see the random write performance is actually going down with queue depth. This is just because the drive is full and it's doing more garbage collection. An enterprise drive handles this random write workload much better, but still 78,000 is not terrible for the 4K random write at these. Now, where the drive really had a tough time was during this 70-30 mix workload. You can see the latencies get extremely high over here. It's just, that's, this drive is not meant for mixed workloads. It's meant for bursty consumer workloads like sequential read and write for gaming and, random reads. This is not super shocking that, that we're seeing this. Now, sequential read, you can see we actually get up to that 28 gigabytes per second, 28.6 gigabytes at QDEP 16. We get real close at QDEP 8. So this is really strong, which means this is the strong point of this drive. It can read data sequentially off the drive extremely fast. Random read is also, random read of large block size, you'll get lots of bandwidth as well. So when I did like 128 kilobyte random read, you also get really good bandwidth like that. And then random sequential write, we're basically even at QDEP 1. Remember, each drive can do about 1.5 gigabytes a second, after the post cache. And so we're seeing the post cache write speed because the drive's already filled up sequentially before we start. We fill up the drive sequentially, and it averages about 7.13 gigabytes per second, which means it started out high and then went low. And you can see sequential write's now about 5 gigs a second. So, this is not terribly shocking here. Again, this is all pretty expected off these consumer drives. Now, I did run some Chia plotting workloads, of course. So I ran a one drive with no cache just to see what the performance would be, and it was 19 minutes for Bladebit disk. And you can see here, if you go look up the average write throughput, 2 gigabytes a second, read throughput 4. But the table too, when the drive is empty, it starts out really fast. This is the SLC cache doing its thing, right? It's the average write throughput 6.5 gigabytes a second, but then it falls down. And so, yeah, if it could only sustain that high SLC bandwidth through the duration of the plot, the performance would be much more amazing. Now, if you add, if I did the 4 drives, no cache, so let's see, I got some interesting data. So I ran the second time I ran, I got 11.2 minutes. The first time I ran, I got something like 8.5 minutes. So when the drives were nice and fresh and clean, they did perform much better. And so that's unfortunate, obviously. Now, the one interesting test I did, which is probably the more realistic use case on a high-end server like this, right? You're never, one consumer drive is not enough bandwidth to sustain 64 threads of this. I'm using R64 for this AMD Threadripper Pro. So if you just look at the cache workloads, when you're caching the writes with 100 gigabytes, you're down to like 12 minutes. And so this is kind of surprising. You still had a decent amount of I/O weight, even on the 400 gigs of writes that this needed to do to complete the plot, with the rest being cached. So that's a little surprising to me. Even with the P5510 and the cache, that performance is much better. I just ran one with the P5510 to compare against with no cache to kind of compare. And, that's pretty similar, 12.4 minutes. Bladebit performance is okay. I think I'll probably have to move this to a system that's a little bit more respective of the class of system I'm on, like a desktop. This is like an insanely high-end workstation. And so likely this many cores is just too much for this. But yeah, really the optimal plotting setup is this 100 gigs of DRAM plus a good NVMe that will get you the best plotting times and really consistent performance across the plotting. So I hope that was interesting, and a look at the RAID performance of the P44 Pro. I do have a few now popped into my Windows desktop, so I'll do some more testing on single drive 2 terabyte SKU and see what we can find out. But with that, thanks.